So basically, in the presence of uncertainty, you get several possible estimates for a parameter. And if you compute the average, you would like to see that the average of these estimates is equal to the true value. You don't want to see a consistent overestimation or a consistent underestimation. Unbiased means that you are indeed, with the average of these estimates, approaching the true value. So an unbiased estimator means that if you get several estimates and you compute the average, it's converging to the true value, which means that these several estimates are not consistently overestimating or underestimating. So as I said, let's go back to our technical, because I went a bit into statistics, because I wanted to tell you, and this is the information that I want to give you, that there are theoretical and statistically based proofs about each of the objective functions. So it's very important. I mean, it's important to make sure that once you devise an objective function, it's important to prove its statistical properties, its large sample properties. But on the other hand, let me go back to the technical field. What I just would like to say is that it can be proved that this objective function that has a good basis from a technical point of view has also good statistical basis under assumptions. Okay, there is to say that these assumptions are not always met in hydrology, and in particular, you may notice one thing, that this objective function is squaring the errors. Squaring means that it gives more weight to the larger errors. Basically, for an hydrograph, it means that it gives larger weight to the high flows than the low flows, because the errors in the simulation of the low flows are smaller than the errors that we make in the simulation of the large flows. Keep in mind, this is something that is intuitive. You can easily get it. If you simulate a flood of 1,000 cubic meters per second, you may get easily an error of several hundreds. If you simulate a flow that is 1 cubic meters per second, you would get at most an error of, I don't know, 10 cubic meters per second, but not several hundreds. So the errors that you make in the simulation of the droughts are smaller and smaller, or the low flows in general, are smaller and smaller than the errors that you get in the simulation of floods. So basically, by squaring these errors, it means that you give larger weight to the simulation of the peak, which is something that is good for us, as long as we are interested in the simulation of the floods. Conversely, if you are interested in the simulation of the low flows, the subjective function is not very good for us. The subjective function in the literature is denoted with several different algorithms, and sometimes I would say that the most used is SS, which is sum squares. And I use the least squares because the least squares solution is the solution that you get when minimizing the sum of squares. So basically what we have to do is to give to our algorithms the sum of squares as objective function, and then the algorithm finds the parameter that leads to get the smaller sum of squares, which is the least squares solution. Okay, but as I said, if you are interested in the drought flows, this is not really good. And therefore, one may think of avoiding the square in order to give more weight to the smaller errors. But if we do that, then we need to avoid compensation, we need to take the absolute value. So let me introduce the second objective function, which is the sum of absolute errors. And basically, it is written in this way. Please allow me to rewrite. I give you the time for copying it. Okay, you may want to get an even higher focus on the low flows, and therefore you may get the idea of getting the sum of the percentage error instead of the sum of the errors. Basically, if you take this absolute difference, basically you are computing the sum of the absolute errors, of course. And if you want to give more weight to the low flows, as I said, you could think of dividing this difference by the observed QT. And this would be the sum of the absolute percentage or relative errors. So let me introduce it. The sum of the absolute relative error. And what you have to do is just to here divide by QT. I give you some time. Yeah?
Is the same SAE or there's
No,
a R?
yeah, sorry. Correct. So usually, okay, let me, let's use SRE, sum relative error. And don't be too concentrated on the acronym, because in the literature you find several different acronyms, of course. There is one potential drawback in this, by using this function, which is the problem that you may get if Qt is tending to 0. If you get very low flows, then of course for these very low flows, the relative error tends to infinity. So one must be very careful in using this objective function if there are river flow values equal to 0. It may happen with the intermittent river flow regime. It may happen that you get some 0 values. But also, if you have very low flows, like 0.1, you get an amplification of the relative error, which is not really good, because then you get an estimate that is not consistent and biased. So you have to be very careful in using this subjective function. It's very good for the low flows. If you're interested in simulating the droughts, then this is very good. But one must be careful about the presence of values that are very close to 0. And okay, I would say that that's it. I mean, there are several objective functions proposed by the literature, a lot of them. Logarithmic objective functions, exponential objective functions, and let's close here, because basically for our purposes, the most important ones are the first, these objective functions that I introduced. And also you can be creative in devising your own objective function. For instance, if you are interested in simulating the river flow, the low flows, you may exclude from the computation of the objective function the river flows above a given threshold. You could include a threshold and exclude them. You can be creative. And as long as creativity is supported by technical considerations, it's fine. I mean, if you get a result that satisfies you and your clients, then it's fine. And I mean, you don't have necessarily to worry about the statistical properties of what you are doing, the statistical properties of your estimate. Because of course, if you are creative, it's very likely that your estimate is not consistent and not unbiased. But you know, it's not a problem as long as you get good simulations for your technical purposes. So for instance, if you are interested in the simulation of the low flows, you may get a very good simulation of low flows and very wrong high flows. So for sure the estimate wouldn't be consistent, because statistics looks at the overall performances. So your estimate wouldn't be consistent, because you would get for the high flows something that is really wrong. But if you are not interested in the high flows, you don't care. Your estimate is not consistent, but for your technical purpose it's fine. So, as I said, as long as you get results that make you happy, that make your design more supported, more reliable, that's fine. Okay? So, as I said, you can be creative, and you just have to be careful, if you are creative, of carefully checking what you get. That's it. I mean, from a technical point of view, you have to be very careful in checking what you get. And if you are creative, it's very likely that you have the experience and the sensibility to make a good check. Because, of course, you devised your objective function, so you gain some expectations on your results, and you look at what the model is doing, so you get, as I said, the necessary experience to make the check. You just have to be careful of checking everything. Okay? Good. So tomorrow we will try to estimate the K value for the linear reservoir by using several objective functions. And we don't have to care about the algorithm that is looking for finding the best value, because the algorithm are something that is given by the statistical package, R in our case, and they are well tested. So, I mean, in the past, seeking the best solution and writing the good algorithm was a subject of, was a matter included, an argument included, sorry, a topic included in the subjects of hydrology. Now, we take this topic for known. It's something that we have. We don't have to care about the structure of the algorithm, okay? Perfect. Let me then introduce another issue related to calibration. With the calibration, what you do is to find the best estimate for your parameters, and you use data. In the case that I discussed with you, we use observed data to find this best estimate. So basically, your best estimate is conditioned to the data. And it means that with, as I said, with a different data set, you would get a different estimate. And if the data set is large, of course, you are happier because you are more confident on the reliability of your data and then your estimates. But on the other hand, it's always true that for a different data set, you get a different estimate. Now, the question is, when we go to application, we apply the model to get a design variable by using a different data set. We are not using the data set that we used in calibration. So basically, we must expect different performances of the model because the model was trained, was calibrated, was optimized with respect to a different situation. An easy example could be if you use data that were collected in spring, in the spring season, it's easy to understand that if you apply the model in the fall season, you get different performances because there are different conditions. So your parameters, your model was trained with respect to a different situation. So the question is, if it is true, and indeed it is, that different data sets lead to different model performances and therefore different parameter estimates, how can I make sure that when I apply the model, which is an out-of-sample application, it's called also out-of-sample, which means out of the sample that has been used to train the model, how can I make sure in this out-of-sample application that the model performances are good? And you could say, but I already calibrated the model. Yes, but we know that your calibration is to some extent limited by uncertainty. So there is a further step that you should make before applying the model, which is to test the validity of the model and the parameters in a real world situation, which means in a real application, before using it for, let me say, the real world application. So basically the procedure should be calibration, testing by emulating a real world application, and finally real world application. So there is an intermediate step that we shouldn't skip. And we shouldn't keep it for the very good reason that we know that our parameter estimate is certainly not the best one for the real world application. I hope it is clear. This in-between step is called validation. Again, it is not described in my notes yet. As I said, I hope next week to complete it. Validation. It's also called verification, but in hydrology it's typically called validation. And there is a huge debate on model validation because, you know, we have few observed data. So what is a proper solution for performing these two steps, calibration and validation? What is a proper solution, given that we have few data? There is a very simple solution that comes to your mind. Let's suppose that you have an observation period between 0 and t covered by observed data. So you have this observation period covered by observed data, which is usually limited. And there is an obvious solution to perform both calibration and validation, which is splitting the sample. And it's called, indeed, split sample validation. What does it mean? It means that you split the sample in two pieces. One is used for calibration. The other one for validation. So you calibrate the model on the first piece. You get a K value for the case of the linear reservoir, and then you apply the linear reservoir model to simulate the second piece by using a K value that you estimated on the first piece. This is the split sample validation. And you must expect lower, poorer performances of the model in validation with respect to calibration. For the very reason that I mentioned to you, that the model was trained for this specific situation. If you use it for simulating an out-of-sample data set, then you get poorer performances. If you get better performances, it must be just a matter of chance, just a matter of casualty. Look, there is a huge debate in the literature because in doing that, you reduce the sample that you use for calibration. And this sample is already restricted, so usually we don't have enough data to safely perform a split sample validation. So people say, why should I do that? Why should I apply a model by using, for calibration, a reduced data set? And this is a relevant question, and the technical solution that is suggested is as follows. You can use the split sample procedure, but first of all, you should also invert the two periods so as to perform two validation, two calibration and two validation. Finally, if you are happy with the solution, before applying the model, you should perform another calibration by using the whole period. And what you would expect is that the estimates for K are not much different. If they are much different, you know, it's a sign of uncertainty, of relevant uncertainty, so you should be concerned a little bit. If they are similar, then it's fine. And of course, when you split the sample, you could split in pieces of different size. So typically people may use only 1/3 of the data for validation. And so you may have more possibilities for performing multiple validations, because if you use 1/3 of the data, then you have 3 possible solutions for validating the model by using the first third, the middle third, and the last third, and so on. But usually validation is considered an essential step. You shouldn't skip it. Okay. Now I have 10 minutes. I would like to move a small step forward to introducing the next Rain-Foranov model, which is the last one. So basically we considered so far 2 Rain-Foranov models. The rational formula, which is not really a Rain-Foranov model, it's a model for estimating the peak flow. And then the linear reservoir, which is a model that it's a real Rain-Foranov model. And then I would like to introduce the next one. And before I move to the next one, let me summarize the fact that the linear reservoir doesn't consider any water losses. Let me recall you. it doesn't consider any water losses, and therefore it doesn't consider evapotranspiration. And let me say, because I forgot to make these considerations, so before introducing the next one, I would like to make some final considerations of the linear reservoir, sorry. So, as I said, it doesn't consider evapotranspiration. It's possible to consider it, because instead of using the gross rainfall, gross means rainfall that is measured at by the instrument, you may use in the linear reservoir what is called the net rainfall. And the net rainfall is gross rainfall minus evapotranspiration. So you have to get an estimate of evapotranspiration and then subtract from the gross rainfall this estimate, therefore getting the net rainfall. So this is a way of considering evapotranspiration in the linear reservoir. Also, let me point out that you could use in the linear reservoir a different relationship, a different discharge relationship, a nonlinear one, for instance. Or you may consider k values varying in time. All of these modifications make the linear reservoir non-linear. And you could introduce other modifications. For instance, there is in my notes an example of, sorry, I get back my notes. There is this example of nonlinear reservoir. If you look at here, you can introduce additional discharges mid-level as you want. You can be creative here. Of course, if you make the model nonlinear, because each of any modification makes the model nonlinear, because look, this discharge here, which is not at the bottom, but it's a kind of mid-level, is introducing a threshold. So you don't have any discharge up to this water storage, and then after a threshold of water storage, you get some discharge. These thresholds make the model nonlinear. By definition, you know, if you make an experiment, if you have a x and y, sorry, a function, x and y, this is a linear function. A linear function is represented by a straight line or a piece of a straight line. But if you get a threshold, which means that your function is formed by two segments, this is nonlinear. And this is a typical threshold. So up to here, you have a certain parameter for the slope. The slope is constant value up to here. After this x value, you get another slope, which means nonlinearity. You see, this function is clearly nonlinear. Linear by definition is, as I said, straight line. So each of these modifications makes the model nonlinear. Nonlinear means that you cannot analytically integrate the model, and therefore you need to solve it numerically. But it's not a problem, we can do that. And how can we do that? It's very simple. If you get your tank, if you get your nonlinear tank, for instance, with a bottom discharge and a mid-level discharge, and you know rainfall Pt, and here you have a, let's suppose, a storage Wt, and here you have a Qt, which is a general function of Wt, which is known but nonlinear. What can you do? Okay, let's suppose that we start from this state of the system, and we want to compute Q T star. So let's suppose that we start from a time T star with this state of the system, W T star, and we want to compute Q T star. This can be easily computed. If you know the shape of this relationship, you can just compute Q T star is equal to F of W T star. This can be easily computed. And then, once that you know Q T star, you can decrease the WT value by subtracting the water volume that flows out at this time step. And then you know rainfall, and therefore from this level you can add the volume of water given by rainfall. So you realize, for instance, and perhaps that at the next time step you get a Q1 T star plus 1 because you have some flow from here. So at the next time step you start computing this flow, and then you compute this flow, Q T star plus 1. And so from here you go down to perhaps here. And then again you add rainfall, and maybe that you get here. So you see that it's easy. At each time step, what you have to do is compute the outflow, subtract from the water volume, add the water volume given by rainfall, and then you get to the next time step. And then at the next time step again, compute the water flow, subtract the water volume, add rainfall. It's easy. It's a very easy numerical integration. But you see the problem here. What is the problem? The problem is that, first of all, the order matters. I mean, I decided that the first operation is computation of the river flow and then subtraction of the water volume given by the outflow. If I decided for a different order, I may have decided for first adding the rainfall. So I get an upper level of water volume, then computing the flow, which means that I would get a higher estimate for the flow because I first added the rainfall. So why we see this apparent inconsistency? This is the approximation given by numerical integration. When you apply numerical integration, you have a numerical error because you are approximating infinite increments, very small increments tending to 0 with finite increments. So basically, when you go to numerical integration, the order of operation matters. And second, you see that you may get the risk of having a water volume that is going up and down, up and down, up and down. And this is instability, which is given to the fact that there are approximations in the numerical integration. And in order to minimize this approximation, you should use very small time steps. But it's easy. I mean, we will see tomorrow, we will solve the linear reservoir in this way. And we will see that if we increase too much the time step, we may get river flow that is going up and down, up and down, up and down. This is instability because it means that the water volume is going again up and down, up and down. And so we will see that we need to reduce the time step in order to get a stable solution. So you see the difference then between numerical integration and analytical integration. With the analytical integration, in principle, you have the exact solution. With the numerical integration, you have an approximation. But as I said, you can be creative and build your own nonlinear reservoir and then use it through numerical integration. So I got to the end of my time, and what I wanted to say, basically, before I forgot to make this discussion, I wanted to introduce the next model. The next model that I will introduce tries to overcome this problem of this instability and threshold effects. And these problems of instabilities are given because, we introduced some thresholds. So once that you get this mid-level discharge activated, then you risk to get an instability because you see that suddenly you have a decrease of the water volume of the water storage because you have an additional discharge that has been activated. So basically the next model tries to resolve this problem, and it will be the last one because the literature proposes plenty of rainfall models, and I would say hundreds, and we try of course to keep our sample limited. So again, tomorrow morning please bring your laptop so we can practice.